So I'd like to start off where I stopped yesterday, or where I screwed up yesterday, to be more precise. So this is supposed to be about decomposing two connected graphs. So the pasting theme we've got in here. So I pasted it from the previous slide, which is decomposing connected graphs. Decomposing two connected graphs. So what we'd like to do is decompose two connected graphs into three connected bases. And the reason I want to do this properly is because I think it might be useful for our purposes. So for instance, if we want to enumerate three connected graphs, it would be useful to know that they have a tree-like structure. Or if we wanted to prove something about the partition function of three connected graphs.
Turn it on.
Oh, I didn't turn it on, sorry.
No, you don't have
It's on top.
Okay. If you want to prove something about the partition function of three connected graphs using deletion contraction, then when we delete it or contract it, we may not have a three connected graph. We may have a two connected graph, and we may want to apply induction to three connected pieces of this two connected graph. So knowing how a two connected graph breaks up into three connected pieces might be useful. So I'd like to try and do it properly. So the idea is we have two vertices x and y, and usually x and y are going to be a two vertex cut. So they're going to separate the graph, and we're going to have several components. There is an exceptional case, which is if we have a multiple edge. So what we're going to do is we're going to decompose into three connected simple graphs. So if we have a multiple edge, then, well, let's call this x1, y1. We call this x2, y2. So I'm also going to pull multiple edges off the graph. So I'm thinking of this as being in some sense also a two vertex separation, even though there is only a multiple edge on one side. So that's the last condition here. So r is greater or equal to 2 if xy is not a multiple edge. But if xy is a multiple edge, then maybe there is only one component in g minus xy. Oh, I've got this funny machine as well. So we've got the idea of an xy component, which I think I called bridge yesterday, because so this theory is due to Tut, and Tut called these things bridges and called bridges isthmuses. So I'm actually going to use bridge for bridge, and so I'm going to call this an xy component.
And isthmus for?
Okay. I have difficulty pronouncing isthmus, so I'm not going to use it for anything. So if we look at, there are three x1, y1 components. So there is the one on the right-hand side. There is the edge. And then there's the one on the left-hand side, which is so there are three x1, y1 components. And this one we call trivial, because it just consists of a single edge or a multiple edge. How are we doing? So given an xy component, for example, this thing, we look at it and we ask, is it two connected? And the answer is no. But then we look at what we get by deleting the vertices other than x1, y1 from the graph, and we ask, is that two connected? And the answer is yes.
I'm sorry, say it again. You look.
So we look at the xy component itself and we say, is it two connected? And we also look at what we get by deleting the vertices in this xy component other than the separating vertices.
You look at just the complementary piece.
Yeah, the complementary piece. So it's the union of the other it's the union of the other xy components. And we ask, is that two connected? And it is. And if either the xy component is two connected or its complement is two connected, then we say it is excisable. I don't really know what excisable means, but that's what Tut called it.
Removable
Sounds like something from a horror film.
Removable or cuttable.
Yeah, okay. So it's
But that's not the same as what you were calling a hinge yesterday?
well, it's an excisable xy component. So this is an excisable xy component, and this is a trivial
I don't know
xy.
what excisable means. What means to excise?
To excise.
To cut
out.
To cut out, yeah.
Cut out.
Literally
yeah.
from Latin to cut out.
Thank you.
Yes, you're right.
So it's got nothing to do with exorcism.
No, that's exorcise.
Yeah, whatever. It's close though.
So again, so a component is called excisable if either it's two connected or it's complementary.
It's two
It's
connected.
two connected.
So in particular, if we have we have at least three xy components, then each of those components will be excisable. Because if we have at least three, then the complement will always be two connected. So the union of two xy components is always two connected.
But the exception is a trivial component is never excisable.
Yes. So, and another example of a component which is not excisable would be if we look at x2, y1 components. Then we have two components. Well, which is the thing I screwed up yesterday? It was this thing, yes?
Any of them.
y1, y2, let's call this x3. So if we look at x1, x3 components, then the right-hand x1, x3 component and the left-hand x1, x3 component, neither of those is two connected. So neither of them are excisable. So if there is an excisable xy component, then we say that xy is a hinge. So the existence of an excisable component makes the corresponding two-vertex separator a hinge. So it picks out the separators which are not crossed by any other separators. Where I'm not saying really what I mean by crossed. So here there are three hinges. So x1, y1 is a hinge. x3, y3 is a hinge, and x2, y2 is a hinge. And the other two vertex separators are not hinges. And we have to make a distinction between hinges. So a hinge is type 2. A hinge is type 1 if there are exactly two corresponding xy components. So this is x2, y2 and x3, y3 are type 1 and x2, y2 is type 2.
X1, Y1.
x1, y1, thank you. Good.
Do you have some light up there?
We had, I don't know. It's strange, there don't seem to be any board lights, eh?
Can you maybe just read it out again?
So x2, y2 is,
No, just read what's written there.
so x2, y2 and x3, y3 are type 1,
Okay.
and x1, y1 is type 2. So now we've got the hinges. The next thing we'll do is we'll construct the three connected pieces. So Tut called the three connected pieces cleavage units. So maybe he was having a little joke. So what we'll do is we'll construct an augmented graph, and we add the augmented graph by adding virtual edges. So for a how do we add virtual edges? So we're going to add virtual edges which are incident with the hinges, and for each hinge and each excisable component of that hinge, we add a virtual edge. And?
So if there are two, so for x1, y1, you add three virtual edges?
No, because the trivial one is not excisable.
I know, but I thought you were saying you add one for the hinge and two for the two excisable components.
No. For each pair, where xy is a hinge and h is an excisable component, we add a virtual edge.
Oh.
So we'll add a virtual edge here, which is E1. And this hinge has, well, it has two pairs, but because it's type 1, we only add one edge. So we'll see why later. So for this hinge, there are two ordered pairs. So there are two excisable xy components, but because it's type, I've got my types? No, because it's type 1, I only add one edge. I don't add two edges. So here I only add, it's type 1, so I just add one edge, which I'll call E3. But now this is a type 2 hinge, and it has two excisable components. So for each excisable component, I add an edge. So I'm going to end up adding two virtual edges. I have E1 and E1 dashed.
The one on the left is E2?
This is E2. Thank you, Alan. So now we pull the graph apart along the hinges, along the virtual edges.
You can have even more, or it's up to 2, no more. Because you can
No,
have
if
more components.
if I had another component attached to these two vertices, then I would add another edge.
So for a type 1 hinge, you add one, and for a type 2 hinge, you add one per excisable component.
Yes. So I'd like to be able to see myself pulling it apart, but I don't think there's room. So first we will pull off the multiple edge. So now we're going to create the cleavage units. So the first cleavage unit will be, I can't see over there. Is it x2, y2? And I guess this is E2. And now if we pull off along this virtual edge and this virtual edge, we'll be left with a cycle of length 5. So we get a... Oh, this is hopeless, eh? I can't see anything. E2, and I guess two edges, and then we'll have a virtual edge at E1 dashed, and a virtual edge E3. 1, 2, 3, 4, 5. Good. What's that? So I'm pulling off this 5 cycle. So maybe it will be. It's time to move on to the next. So we pull the graph apart along the hinges, and the cleavage units are the minimal graphs in this pulling apart operation. So let's draw this a bit differently. So next cleavage unit, we have the original edge in the graph. This was probably E1 dashed. We have E1 dashed, and we have E2 dashed.
E1.
E1, thank you. And then we will have E1 and this thing. And now we pull it apart here, and we'll have E3 and this thing.
So what is the precise definition of these cleavage units? Can you explain this?
Well, I guess I'd like to try and define them recursively. So I take this virtual edge, this hinge x1, y1, and the virtual edge he1, and I cleave the graph along that virtual edge. So it will give me 2 pieces, one of which will be the rightmost cleavage unit, and the other one will be this graph. So with a triple edge here, and then I just keep on progressing recursively. So next I can pull off this triple edge, and I'll be left with this graph, and then I would pull off this piece, and I would be left with this and the triple edge, and then I pull off the triple edge.
You cannot do it in one step. You simply cut
Yeah.
every virtual edge into 2 somehow. You
Yes.
really split it.
Yeah.
Well, you say make 2 copies for every virtual edge.
Yes.
And put them in different pieces.
Yeah. So the tree structure is obvious. So the cleavage unit tree we get so the vertices of the cleavage unit tree are the cleavage units. So we have and the edges of the cleavage unit tree are the virtual edges. And each virtual edge is incident with exactly 2 cleavage units. So we end up with the tree D1, E2, D2, D3, E1, D4. Oh, sorry, this was E1 dashed, E1, and then D5 is joined by E3 to D2.
Can D3 and D4 be exchanged in this tree? It seems like you rely on a planar representation.
Sorry, can D3 and
Like in the chain that goes to the right in the tree, why D? I mean, is there an ambiguity? Like, can D4 come before D3?
no. So these are different virtual edges. So
Yes, but
so
the order is
Why do you put E1 prime to the left and E1 Do you use the fact that you draw it on a plane, or?
No. So D3 is adjacent to D2 because they share a virtual edge. So I had one virtual edge for each excisable component, and the virtual edge E1 dash was the one that was in common with. Well, I guess I've got the D2 and D3. So it's a unique tree decomposition. And so this is a theory, as I said, developed by Tutt. So he showed that the cleavage unit tree of a two-connected graph is indeed a tree, and each cleavage unit is either a three-connected simple graph, or it's a cycle, or it's a multiple edge. Yeah?
D4 is not three connected.
Oh dear. Now it's D5.
You just have to make your tree a bit bigger.
Yeah, I don't want to make my tree bigger. I want to add some more edges. I'm going to be around there.
X1, Y1 has got
So
four
X1, Y1 has four
components.
four
What?
XY components, because these are different components. They're not the same component.
What's it again? Oh.
So
If you delete X1 and Y1, you get three connected components.
So I delete this two vertex cut. I don't get one component. I get two components.
Oh.
So that is a component, and
So add
that
this.
is a component.
Add this edge on the end.
Yeah. So I to do this graph, I would have triangles coming in as so, but I don't want to do that. So I'll add these edges. And it'll be okay.
Bravo. So,
Is that okay, Roman?
No, there is this order D2, D3, D4. It sounds like, really you can exchange D3 and D4. Why they are in this order? Because somehow at this edge it splits into three, and which two somehow share this virtual edge.
But D3 has two virtual edges.
Why?
D,
This is, you have.
So here the virtual edges are. So if
Also
D3
D2 and D4 should share a virtual edge somehow.
if it's correct that D3 has two virtual edges,
But
D2 and D4
imagine that you draw this D4, this line you draw like that, around all this graph. Yeah.
No, but Roman,
Why not?
But the point, no, but it doesn't matter who you draw it. The point is,
Yeah.
if it's correct that D3 has two virtual edges, and D2 and D4 each have one, or at least D4 has one, then D3 has to be the one in the middle, right? If D4 has one virtual edge, it has to be a leaf of the tree. So the question is, why does D3 have two virtual edges?
because it's a trivial component and it's kind of attached to two excisable components. The virtual edges are associated to excisable components. And
But
then,
they're
then you
also-
pull off the excisable component and you leave a copy of that virtual edge behind.
So you get a virtual edge either if you are an excisable component, or you get a virtual edge for each excisable component of your complement. Is that right?
Yeah. So each non-trivial component of a hinge gets a virtual edge.
But also the complement do. Right, because each of these virtual edges get copied. Isn't that right? I mean, once you draw the cleavage units.
Well, once you pull apart, the virtual edges get pulled into two.
All right. But you have to figure out where you pull them. I mean, the whole question is, where does it get pulled? Where do these two copies get put?
Well,
Because of the tree structure, it doesn't matter where you pull it apart first, right? Because it's a unique decomposition.
yeah.
That was a clever guy.
Yes, for sure. So I was going to do another, a smaller example because I thought maybe it would help, but I don't know whether it helps. I'll do it anyway. So if we try to pull this graph apart, we would get, we would add 4 virtual edges. And the tree we would get would be a star. So the end vertices would be 4 triangles, and the vertex in the middle would be a multiple edge of size 4.
All virtual.
All virtual, yes. Yeah?
So would it be accurate to say that that in the decomposition, okay, for each name of a virtual edge with that name occurs exactly twice. One in one component, and the other in the other component, and then you get the original graph back. If you glue all the corresponding virtual
Yeah.
edges by pairs, and then delete them.
Yes.
Okay, and then furthermore, each component counting its virtual edges, right, is either a cycle length greater than or equal to 3, or is 3 connected?
Yeah, or it's a multiple edge with at least 3 edges. Then that depends whether you think of that as 3 connected or not.
But here on this picture, there are not excisable components at all. Nothing is to connect it.
Yeah, so you mean
No,
each of the cleavage
on
units?
this triangle picture on this one.
Yeah. Yeah, all the triangles.
Are not excisable.
Oh.
They are not excisable.
So this, yeah, each of the triangle is excisable because, this is not a 2-connected component, but its complement is 2-connected. Its complement consists of 3 triangles, of K2-3, I guess. So each of the components is excisable. So that's
Next
the end of the
step.
first talk.
Next step, you're going to decompose 3 connecteds into 4 connected?
Well, that's problematic because the 3 vertex cuts can overlap too much. So it's not a tree-like structure. So James Oxley and is it just James and other people, I think, has a theory of decomposing a 3-connected matroid into 4 connected pieces.
Yeah, that was with me.
Well,
And
so
actually-
Jeff will talk about it on Thursday.
I don't want to. But it does imply that you can decompose a graph in a tree-like way, and algorithmically, efficiently too, I think, but into vertically 4 connected pieces, or internally, or some, like, you're not exactly 4 connected, but you're very close to being 4, and you can do that.
So for instance, one of the pieces could be a 3 regular graph in which all 3 vertex cuts are trivial in the sense they just leave 1 vertex on one side.
But it's not, the decomposition's not unique, but in some sense it doesn't matter because you can record what you've done efficiently, so you can recover the original graph efficiently. So it's not a drama.
So for our purposes, I think what we'd like to do is quite often is reduce a vertex of degree 3. So we'd like to split off a vertex of degree 3. And then that theory won't do that because it wouldn't it wouldn't consider such a cut as a 3 vertex cut.
No. You're forced to be left. You can't decompose off a single vertex of degree 3.
Yeah.
Excuse me? If you work with the notion of connectivity with respect to edges instead of vertices, is it much easier to define higher, like 2, 3, 4, 5 connected?
Yeah, you can decompose a k edge connected graph into k plus 1 edge connected components.
Because you can take like the maximal subsets which are k connected and it forms a partition, which is like, I guess, vertices.
Yeah, I guess if you define an equivalence relation by saying 2 vertices are equivalent if they're joined by k edge disjoint paths, then that would be the partition of the vertices.
So edge connectivity, this decomposition theory works more nicely.
Yeah, it's not exactly the same, but it works for all k. Yeah. So there is a general theory for decomposing structures due to Cunningham and Edmonds.
And might this edge connectivity decomposition be useful for the kinds of applications we have in mind for chromatic polynomial, polynomial?
Well, we need conjectures which involve edge connectivity, and I don't think we have any. It seems to be that vertex connectivity is the thing that matters, but
you can compute the type of polynomial of the graph, the polynomial time which the graph has bounded tree width, and like having, say, it's tree width less or equal to k. And so tree width less or equal to 2 is the same as being series parallel. So tree width less or equal to k means that you've got a tree-like structure of a lot of less or equal to k separations.
Vertex separation.
Vertex separations, yeah. So that's actually telling you that having a lot of small vertex separations is really computationally a lot of power. But I don't think there's an analogous result for edge separation.
If you have edge separations, don't you automatically have vertex?
I suppose that's
separations?
Right, but I just haven't. I never think about these separations. But anyhow, like that is the thing, that it doesn't really matter. So you can go from 2 to something higher, and you still, knowing that you've got a lot of small separations in the graph, still tells you that the graph somehow is tree-like in some way, and you can use that.
So I think I'd like to cut to the chase in my second talk. So I was going to talk about matchings and independent sets and vertex coloring and floors, and then talk about chromatic polynomials and floor polynomials and Tut polynomials and the partition function. So as you can see, I was a bit over optimistic. So maybe what I'll do is I'll skip to just telling you what a floor is, because I would like to talk about floor polynomials, and maybe people are not familiar with nowhere zero floors. So unless anybody objects, I won't talk about vertex coloring. I'll assume that everybody knows what a proper vertex coloring of a graph is. Is that okay? As you can see, I've got 68 slides. So maybe we'll go at the end and work back up. Good. Sorry about that. So I'd like to start off talking about nowhere zero floors in graphs. So we have an undirected graph J, which is, I always end up drawing the same graph, the Harari graph. And so for a flow, we need to give it an orientation, but the orientation we give it is just for reference. So the orientation that we choose does not really matter. So let's choose an orientation. No, I don't think I want that one. I want that one. And now, so I'd like to have so now I have an abelian group, gamma, and this is my graph G. So let's take gamma to be the integers modulo 3. And what I'm going to do is I'm going to put the elements of this group on the edges such that at each vertex the net floor is 0 in this group. So I can put 1 here, and 1 here, and 1 here, and that'll force me to put a 2 here, and it will also force me to put a 1 here. So this is an example of a Z3 flow. So here we have the flow in, which is 1 plus 2, which is 0 mod 3. So the floor is, so this is saying that the flow in is equal to the flow out at every vertex. If the floor is non-zero everywhere, then we say it's a nowhere zero floor. So there is a trivial floor which we can get just by putting 0 everywhere. And a nowhere zero floor is the other extreme. We have no zeros. So this is a nowhere zero Z3 floor. So just by conservation of floor, the property that at each vertex we have floor in equal to flow out means that at each edge cut we have the net floor across the cut being 0. So for this edge cut we have 1 plus 1 minus 2 is 0. So the definition of the floor, the property of the floor that at each vertex we have net floor gives us the stronger property for all the edge cuts the net floor is 0. And in particular that means if there's going to be a nowhere zero floor, then the graph had better not have any one edge cuts, which we'll call a bridge.
Or an isthmus.
Or an isthmus, if we can pronounce it. So if a one edge cut separates the graph into 2 pieces. So this is a bridge. And if no matter which orientation we choose or which group we choose, by this edge cut property, if we have a floor in that group, then we'd have to put 0 on this edge. So to have a nowhere zero floor, the graph must be bridgeless. And if we reverse the orientation of an edge, then we can just replace the group element by its inverse. So this is why I said really the orientation does not matter. So the number of nowhere zero Z3 floors is going to be the same for every orientation. So this is, we can also look at integer value floors. So for an integer value floor, for a nowhere zero 3 floor, we'd use, our group would be the integer z. For a 3 floor, a nowhere zero 3 floor, we could only use plus or minus 1 or plus or minus 2. So now we're restricting ourselves to using only some of the elements of the group. And Tut showed that if there is a nowhere zero K-floor, then there is a nowhere zero Z K-floor.
But there's no relationship between the numbers of such flows?
Well, there are inequalities, but there's no obvious way of getting the number of nowhere zero Z K-floors from the number of zero K-floors. And Tutt also showed that in fact the number of nowhere zero gamma flows doesn't depend on which group gamma we choose, it just depends on the order of the group.
Bill, could you
Yeah?
put this back to full screen?
I could if I knew how to do it.
Control L.
Click on the thing which is in grey up on the top with 4 arrows going out in all directions.
If you press that Control L.
Control L. Thank you.
Yeah.
I feel in your examples, the left upper vertex, how this reveal?
Sorry, Terry?
The left up vertex.
This arm?
No, the first one. Yeah, how this reveal?
It has a flow
It's
up.
0 mod 3.
Which is
We're
0
working in
mod
the
3.
integers modulo 3. So if we but if we wanted an integer floor, then that would not be a floor. We would have to change some of the ones into minus ones.
But the theorem says there's some way to do it.
Yes.
Oh, wait a minute. No, the theorem doesn't say that you can get it just necessarily by changing ones to minus ones. You might have to do. Oh, sorry, here there is only one. Okay.
So this is the point that Alan made, that although the existence of an integer floor, a nowhere zero integer K floor is equivalent to the existence of a mod K floor, the actual numbers of floors is different.
Are you going to discuss the inequalities really?
No. And so a trivial example would be this graph. So the number of ZK floors, I think, number of Z2 floors is 1. We just put 1 everywhere. And the number of plus or minus 1 floors in the integers is 2, because we can have plus 1 minus 1 or plus 1 minus 1.
A number of special cases on regular lattices, say the square lattice or something like that, look like models which are being studied in statistical physics, right? Do you have some list or something of what is known, how many?
I have a list of what's known by graph theorists. I'd be interested in a list of what's known by physicists. So, so the idea of floors was of nowhere zero floors, again, is due to Tutt. And his motivation was that for planar graphs, it's dual to the idea of a proper k-vertex coloring. So for a planar graph, the original graph can be properly k-vertex colored if and only if its dual has a nowhere zero floor.
And here there is essentially a bijection.
Yes.
Right up to some factor of k or something.
Yeah, yeah. But only for you. There is a bijection if you talk about a ZK floor. So the bijection works for mod K floors. It doesn't work for integer floors. And, well, there are two big conjectures in graph theory due to Tutt. So being bridgeless is a necessary condition for any nowhere zero floors. By the previous slide, the four-color theorem implies that every planar graph has a nowhere zero 4 floor. So Tutt conjectures that the four-color theorem is almost true for all graphs, for floors. So it's not true that all graphs have a nowhere zero 4 floor, but he conjectures that they have a nowhere zero 5 floor. And the second conjecture is also inspired by a planar result. So there's a planar result of, is it Groschel, Carsten? Grötschel. Grötsch, thank you. that if you have a planar graph which has no cycles of length 3, then it is 3 vertex colorable. And this is the dual statement. The dual statement would be that if you had a planar graph without any 3 edge any 3 edge cuts? Yeah. If you have a planar graph without any 3 edge cuts, then it has a nowhere 0 3 flow. And so Tut conjectures that the dual statement is true for all graphs. And these results have been proved by Gégère and Seymour up to a factor of 1. It's not a factor, an additive constant of 1. So the first result was due to Gégère, who showed that every graph has a nowhere 0 8th flow. And the trick is to actually use groups rather than integers. So for an 8th flow, Gégère proved there was a Z2 cross Z2 cross Z2 flow. And Seymour showed there is a Z2 cross Z3 flow. And the problem with 5 is it's prime. So there's
And the second Gégère result, you use Z2 cross Z2?
yes. So in fact, it's the same as showing that for any 4-edge connected graph, you can cover the edge set with 2 Eulerian subgraphs.
But of course, we know that the number of, let's say, Z2 cross Z3 flows is the same as the number of Z6 flows.
Yes.
Right? And is there an algorithm is there a natural bijection? Because if there were, then Seymour's proof could be translated into a construction of Z6 flows.
Well, it's the same group.
Is it?
Z2 cross Z3 is just Z6. As a group.
Right,
Oh,
so-
I see. In that case, it's the same.
Yeah.
Oh, I see.
Sorry.
So, but so it wouldn't give you intuition about how you might get a Z5 flow.
Well, people have looked at trying to get a special. So but it is constructed by constructing a graph, an Eulerian graph, which has a nowhere 0 Z2 flow, and showing that you can find a graph which has a nowhere 0 Z3 flow, which covers the edges which are not in the Eulerian subgraph, and then you take the Cartesian product of the flows. So people have tried to show that you can find a graph which has a special nowhere 0 3 flow on the other subgraph, and it's so special that in fact it gives you a 5 flow. People have tried that, but it's
In the previous slide, was it a ZK flow, a Z mod K flow, or a K flow? At the very end in this statement about colorings.
Equivalent.
A K flow, not a Z mod K flow.
well, the existence of a K flow is equivalent to the existence of a mod K flow.
Oh,
And so because
okay.
this statement is just about
Okay.
existence, they're equivalent.
Okay.
But if you want the actual numbers of flows, then it should be a mod K flow.
Okay.
So it would have been better to write a mod K flow. So finally we get to...
The conjecture were only for planar graphs or for general graphs?
Sorry?
The theorem and the conjecture were for any graphs,
Yes.
but the equivalence with the coloring is only for planar graphs.
Yes. So the surprising thing is that the coloring, if you go from planar graphs to non-planar graphs, things change drastically. But it seems that flows don't.
Another way of saying it is the theory of flows on general graphs looks a lot like the theory of coloring planar graphs.
Yes. So one kind of intuitive reason of for what's happening is that in a planar graph you can find a basis for, if you take the faces, they give you a basis for the cycle space, which covers each edge at most twice. And if you make the dual statement, so if you want to cover if you, instead of covering with cycles, you want to cover with edge cuts, with core cycles, then the same statement is true for all graphs, because you just take the stars centered on each vertex. They give you a basis for the core cycle space, which covers each edge at most twice. So chromatic polynomials, if we define Pj(t) to be the number of proper t-vertex colorings of a graph J, then this gives us a polynomial in T, and it satisfies the famous dilation contraction lemma. We can do the same thing for floors, so we can define Fj of T, which is the number of nowhere zero mod T floors in a graph. And again, we have the dilation contraction lemma. And for planar graphs, we have this thing which we've already discussed, that the number of nowheres, the number of proper T vertex colorings of the dual is equal to T times the number of nowhere zero mod Z mod T floors in the original graph. Now this is not true if we use integer value floors. If we use integer value floors, we do not have the dilation contraction lemma, and we do not have a polynomial.
So it means the group value flows are a lot more natural for counting.
I think so, yes. The Tut polynomial is a polynomial which generalizes lots of polynomials. In particular, it generalizes the floor polynomial and the chromatic polynomial. So you can define it by this closed formula. So we have a graph, and for any subset of the edges, we'll use k there to be the number of connected components in the subgraph we get with vertex set V. The vertices of the whole graph, and edge set, just the edges in the particular subgraph A. Then the rank of this set of edges is the number of vertices in the graph minus the number of components. So this is the actual rank of the cycle matroid of the graph, which maybe Jeff will mention. And the Tut polynomial is the two-variable polynomial given by, well, that's the closed formula for it. So it's rather strange, it still seems strange to me that we have x minus 1 and y minus 1 rather than x and y. But I think Tut, there is also a precursor of this, which was the Whitney rank generating function, which did actually have x's and y's instead of x minus 1 and y minus 1s. So Tut introduced the x minus 1 and y minus 1, I think partly to have this dilation contraction lemma.
Because he defined it differently.
Yes, in fact, Tut actually defined it by the dilation contraction lemma, and then showed that this gives a unique polynomial. It doesn't matter which order you do the dilations and contractions.
Well, initially he discovered it by an even worse method.
And what was that?
Activities, internal and external activities.
Oh, yeah.
Where you
That's actually
introduce
a better
this.
method. It depends if you stand upside down.
So I think another reason that Tut another reason that Tut, if you look at the first bullet point, I think one of the things that Tut liked was duality. So I think he liked the fact that if you have a graph and it's dual, then you get the Tut polynomial from the other by interchanging the variables.
Isn't that true for a general matroid? That if you
Yes.
go to the dual matroids and that polynomial flips?
Yes,
Get more matroids out.
but we haven't done matroids yet. So here's some properties of the Tooth polynomial. So it's multiplicative on disconnected components and also on blocks. So if we have two pieces of the graph which intersect at the cut vertex. We have the chromatic polynomial and the floor polynomial, which are actually not so pretty. Those identities would be nicer if we used the rank generating function, I think. And there are special values of the Tooth polynomial give us many properties of the graph. So it gives us the number of spanning trays, the number of acyclic orientations. This is a result of Stanley. And the number of totally cyclic orientations. So an orientation is totally cyclic if every edge belongs to a directed cycle. So finally we get to the partition function, or the multivariate Tooth polynomial. So the Tooth polynomial was a two-variable polynomial. Here we have a mod e plus one variable polynomial, and we have one variable q, which corresponds in some sense to the number of colors. And then the other variables correspond to edge weights, at least to me. And we sum over all subsets of the edge set of the number of colors raised to the same thing, the number of components in the subgraph, and then take the product of the edge weights in that subset. And we have a dilation contraction lemma which doesn't need the special cases of loops for loops and bridges, but for loops and bridges it's actually a bit simpler. So it looks a lot like the Tooth polynomial with more variables, and in fact you can get the Tooth polynomial from the multivariate Tooth polynomial, but it's not so pretty. It would be prettier from the rank generating function. The rank generating function, we would just take all of the weights to be equal. And my final slide is supposed to show that, so this is the Fortuyn-Castellan expansion of the partition function. It kind of shows you that it's the relationship to coloring. So I guess so this is saying that the partition function which we had on the previous slide, we can get by considering all colorings of the vertices, so all colorings of the vertices with Q colors, but not necessarily proper colorings. Point up here, So sigma is a coloring of the vertices. Each vertex is colored either 1, 2, 3 up to Q. And then we take a product of weights of edges, but the weight of an edge depends on whether the end vertices of the edge get the same color or different colors. So if they get the same color, then the Kronecker delta thing is 1, so we get weight 1 plus WA. And if they get different colors, then we just get weight 1. So if we put WA equal to -1 for all edges, then this is just counting the number of proper Q vertex colorings. Because if the end vertices of some edge gets the same color, then the thing in the last bracket will be 0. If the two end vertices of A are the same color and WA is -1, then we get 1 plus -1, which is 0. So we have F, G, Q -1. So this is supposed to be assigning a -1 to each edge weight.
ZG.
ZG, thank you. or even zj, is just the chromatic polynomial of j. So it's a nicer relationship than the one that we had for the Tut polynomial. So I'd like to stop there. Yeah?
So you said with the Tut polynomial, when you specialize it to 1, 1, you get the number of
Spanning trees.
spanning trees. So does this Potts formula, does it give you some sort of the sort of sum of weights of spanning trees if you imagine weighting the edges? So if you have a spanning tree where the edges are weighted, you define the sort of state of that spanning tree as just the product of all of the edges.
Yeah, the answer is yes. Yeah. From this multivariate Tut polynomial, by taking q goes to 0 in various ways, you can get the multivariate generating polynomial of spanning trees, but you can also get the multivariate generating polynomial of spanning forests, and you can also get the dual thing, the multivariate generating polynomial of connected spanning subgraphs.
Are you going to do that this afternoon?
Or Thursday maybe I'll do that. So you can see, you can get, so as q goes to 0 limits of this, you get a bunch of things, all multivariate. And one other thing that's worth saying, the same way that Bill pointed out here, that setting all the weights to -1 gives you the chromatic polynomial, it's also true that setting all the weights to -q gives you up to some factors the flow polynomial. So this multivariate Tut polynomial includes the chromatic and flow polynomials as very special cases.
Somebody disagreed with what you said.
All right.
Celebrate.
Yeah, I think the only bad thing about it, in contrast to the Tut, is that you lose the duality thing. So the duality relationship is not so nice.
There's some kind of duality for the Z.
Yeah, he's gone now. I think we put.
Well, replace, what is it? Replace W by Q over W.
Yeah. And then you have some multiplicative factor coming on the front as well.
Going back to what I said, ask. I mean, if that's the case, that you, on sort of this Q limit, that you get this weighted weighted version of spanning trees. I mean, it's known. I think that there are determinantal formulas for those. So, is there a determinantal formula for this thing?
Yes, I was planning on talking about that soon.
So there's some sort of.
It must be hard to work it out, eh?
No, it's a simple modification of the matrix tree here. Yeah.
But not to work out this thing. This must be horrible.
Oh, to calculate that? Yeah, of course.
As a polynomial.
It's uncomputable.
Yeah.
But
So
there is a
it's hard to
determinant formula. There is a determinantal formula for the generating function for spanning trees that you're talking about.
Is it of this sort of Lindstrom type formula? These
No.
types of sums of products often sort of show up as determinants of matrices which encode paths in some graph.
If you can wait for an hour and a half, probably better to ask that question then.
Yeah?
Is there a characterization of the graphs is that polynomial is symmetric?
Planar self-dual is not a characterization. There's probably some example that's not planar
I'm
self-dual.
extremely surprised if such a characterization exists. The Tut polynomial is pretty coarse in bearing the graph.
This is a classification which is kind of cutting too many graphs into.
That would be my guess.
Except the plane dual, for the surface, do you have some that kind of, you can also draw the dual graph over there on the oriented surface?
Yeah, you could draw a dual graph on an oriented surface, but it's not. The faces don't span the cycle space, so you don't have the duality between the polynomials.
Well, yeah, of course, but the homology should be considered there.
Sorry?
The homology, the cycle, the homology of the surface.
Yeah.
Yeah, I did something like that, but I did, okay, just add homology over there, then you get, okay, also kind of dual.
And does it give you anything on the polynomial?
Well, you
The
don't
polynomial?
consider partition function yet. It's just to talk about the flow and the chromatic. It's kind of thing, okay. There's another factor of the homology there between flow and chromatic.
Oh yeah. Oh, that's interesting.
Okay, well, it's
Tea time.
tea time.